Welcome everyone. In this video I'm going to do something which is based on one of the viewers' idea. So as you can see, I have a quite complex system on the table, but it just looks complex, but it's not that complicated. So let us see what is here. So let's start from here, because this is the core of this experiment. So under this heatsink, which is connected to the cold side of the Peltier cooler, there is a TEC 12715 Peltier cooler, so it's a 15 ampere unit. And then on the other side of the Peltier cooler, which is the hot side of the Peltier cooler, there's an aluminium water cooling block. And as you might hear it, the pump is already running. So I'm circulating the water in the system to equalize the temperature everywhere. So the water comes in this hose on the other side, and then it comes out here, goes through this flow indicator, which has a thermometer, and the thermometer is showing the temperature on this display. So now it's 25.5 degrees Celsius. And then the water goes out and does a loop there. I can get rid of the water here in this valve. So it comes back and goes into this water tank. And then under the water tank we have the pump, and the pump pushes the water into this radiator, which is a 25 by 12 centimeters radiator with two 12 centimeters fan. And then the water comes out on the top of this radiator and comes through this hose here. As you can see, it does a loop and then it goes up here. And here I might try to adjust the camera. Now it's better. So up here we have a TEC 12706 unit. The hot side of the unit is attached to this CPU cooler, and the cold side of it is basically connected into this water circuit through an aluminium water cooling block. It's the same cooling block that I'm using here. And after the water is perhaps being cooled by the Peltier cooler, then it comes out, does a loop, and enters the large performance or high performance Peltier cooler. So what the idea was is that if we have a closed loop cooling system, for example for a gaming computer or something like that, then can we further bring down the temperature by putting a Peltier cooler in it? And basically this is what we have here. So the Peltier cooler there is inserted in this circuit, so it cools down the water, or perhaps cools down the water before the water enters to the thing which we really want to cool, and this basically simulates your CPU. Here we have a 30 volt 12 ampere power supply, so this is a high performance power supply, and I will run this high performance Peltier cooler with it. The goal of this now is to just generate as much heat as possible, so I will run it really close to 12 amps, so or even 15, so on the maximum performance. We will see how it reacts to the current and voltage, and then we will see what will be the equilibrium temperature after, let's say, 10 minutes. We can check the time here. And after 10 minutes, I will turn on this fan first, which is a high performance fan, which starts to circulate the air, and then I can make sure that the Peltier cooler up here will be cooled sufficiently. So then I turn on the Peltier cooler as well. It's a 6 ampere unit, so I will run it at, let's say, 4 amperes. And we will see how the temperature changes here. So it's a relatively basic experiment. And now it's just a few comments. So this is the only way I could assemble this experiment. So now there is a small, very negligible amount of passive cooling of the water here as well, because basically what we have here is a water cooling block connected to essentially a radiator, but the heat conduction through the Peltier is a bit, let's say, limited, so the passive cooling is negligible in this case, even if the temperature is higher, so there is a higher driving force due to the temperature gradients, I would say that it's negligible as compared to the work done by that thing. So also I have 4 different thermometers, and those are connected to this box on the bottom right corner. So one thermometer is here, as you can see. So we will just measure the temperature here. It will be -10 or something. Another thermometer is there, so that will measure the rejected heat indirectly, of course, of the 6 ampere unit. So basically the temperature of the exiting air here will be measured. Another is measuring the room temperature, which is 26 degrees. And the last one is on the other side of this cooler right there, measuring the exiting air temperature. So now I turn on this power supply first, and then I will connect this guy, and also we can always check the current with this. So I will try to connect in such a way that I will have access to the wires, so I can measure the current. So everything looks fine. So now I just slowly start to increase the voltage, because I already turned this to the maximum, to the current. So we are now just controlling the current with the voltage. So this is now 9 amps. Let's make it 11 amps, and we will see what happens. So I can already see that the temperature here drastically started to drop. It's 12 degrees Celsius right here, but you can also see that the exiting temperature now it's 27 degrees instead of 25. So this has reached 0 degrees. Now it's -2 degrees. And I can also see that the other side of the radiator now is at 26.7 degrees read from this display. So the air already started to warm up. And also I can, so -8 degrees right now, -10, once again, and seems like I have to repeat this in every video. This heatsink is in a very weak contact with the surrounding air, and that is the only heat which is entering the cold side. That means that the cooling power is really low in this case, and that also means that if the cooling power is low in this case, then the DT, so the temperature difference between the hot side and the cold side, is large. So when you see that people can reach, let's say, these kind of temperatures, -11 or even lower, that means that they cannot cool with that certain setup, because then the larger the temperature difference between the two sides, the lower the cooling power of the Peltier cooler, and then this is basically what is happening. So that's just one thing, that you can reach very low temperatures, but if you can reach very low temperatures, that also means that you cannot cool properly with this thing, so you cannot transfer the heat from the cold side to the hot side. So now this thermometer also shows -9.3 degrees. You see that this is 30.2, and the air temperature on the other side of the radiator here is 29 degrees now. So I think this looks stable, so let's go up to 12 amps. Hopefully nothing will be damaged. I just want to generate as much heat as possible, and then I want to heat up this water really nicely. So then the change will be more noticeable if there is any change. And for this particular Peltier cooler, I will use the power supply down here, because I will not run it at maximum power, and I just want to run it around 4 amps. And since this is a 12 volt power supply, by limiting the voltage I also limit the current which is running through the Peltier cooler. So based on that, this will run in the optimal cooling range. So now it's -6, and now we can answer the question for that. Why it is -6? Previously, with lower current, it was -10 almost. So the reason for that is because if you haven't checked my previous videos, please check it. But the reason behind this is when you start to increase the current, the minimum temperature that you can reach with the Peltier cooler without any kind of thermal load is increasing. So the reason behind the increased temperature here is because we increase the current, and that is more Joule heating. And then now the Joule heating started to overpower the Peltier cooling, so therefore we started to warm up this. We can still cool with this thing, and in principle the cooling power increased, but the minimum achievable temperature, so the lowest temperature that we can get, got higher. So instead of, let's say, -10, we got this -6 or -3, because simply just we started to heat up the thing with the Joule effect. Okay, so now it's -7 point something, 7.9, depends on how I measure. So it went back to -10, so maybe there was just an initial kick, and then we needed to balance for that. But regardless of this, this always happens. So after a certain point you increase the current, and because of that you will heat up the device. I'm just checking the cables. This is like slightly warm, but it's okay. I can hold my fingers on it. And then of course this is a very big cable. I think it's 6 square millimeter. So this will never be hot by this current. So now you have 33 degrees. Maybe I can go to 13 amps just to give more heat. Let's see. Meanwhile, I can show you something interesting. I just need to bring something here. I saw it in some YouTube videos that people were complaining that they got fake Peltier coolers, and actually I had to disassemble this thing and reassemble it, because I managed to get a fake Peltier cooler. And actually what I got is, instead of having a 15 ampere unit, that unit was a 6 ampere unit with 15 ampere unit characteristics printed on it. What I mean is that I can show it. So here you can see 2 Peltier coolers, and you can immediately see the way they printed the numbers on it. So this looks like more like a laser or thermal printing, and this looks like more like a, I don't know how the technique called, but when you print the ink on it with some sort of pressing against it. And actually the fake one is this guy. So I removed this from this system, because what I noticed that I started to increase the voltage, and when I reached this kind of voltage, 15 watts, the thing was only running at 6 amperes. And you can guess it from the characteristics written on the datasheet that at a certain voltage you should know how much current you can expect. And as you can see it here now, this is not a fake unit, so we are almost at the maximum voltage defined by the manufacturer, and we are almost at the maximum current defined by the manufacturer. So first thing is just always check your Peltier coolers, and you have to see what is the type of the fonts. So this looks crappy, so you can expect that this might be fake, and you can see this is fake, and this is like more professional. You can see that the printing on this is more better. And also what I noticed that if I compare these, I don't know if the video gives it back, but this is thicker, the fake one is thicker. It's just basically the same thickness. The difference is between just an extra layer of this ceramic plate, but that's enough just to spot it. So first thing, check the font, and if you have this let's say smoother font and not this laser or thermal printing, then you can suspect that this is a fake unit. But also cool it nicely, cool the hot side nicely, and bring the power supply to 15 volt. And if you see that around 15-16 volt you have 6 amperes, for example, then it's a 6 ampere unit for sure. And if you see that around 15 or more like 16-17 volts, you should see what is the current, and that is the unit, basically the 2 or 1 less digit. So I hope I explained it in a proper way, but what I try to say is that you have to be careful, because it's not only that these things are not providing the same performance that they should, but they might be also lower quality things. So that is dangerous. I mean, it can harm you or just burn down your setup or something, so don't risk it. So let's say this is some sort of equilibrium, or at least we went up by 10 degrees with the water temperature, so at least we can try our experiment. So this will be noisy, so before that I explain everything, and then I will just move around here and there. So I will connect the power supply of the fan. The fan will be noisy, and after that I turn on this power supply and bring the current roughly around 4 amps, and I will measure it and show it to you, so you will be able to follow it. So I also turn on the power supply. So power supply is on, we will use this side. So let me turn on the cooling. And this is now at 4 amps, 4. So now as I blow the air here, actually this side started to have more interaction with the environment, so the temperature of this started to increase. As you can see. But the temperature there is still 26.7 degrees. So now you can see here a slight decrease in temperature, which is like 0.4 degrees Celsius, but that's not too big. So this temperature is actually this side, but if I measure it here, and it's warmer. So this. So now we have like 0.5, 0.7 degrees drop. But for this small drop, we had to convert this system to a new system, so we had to add this wall cooling system, and I think that's a huge sacrifice. And also I have to emphasize that this is a high performance fan, so this is probably, if you decide to use water cooling for your PC, you don't want something this loud. So what I want to suggest that maybe without this fan and with some more regular 12 centimeter fan, you would not be able to run at the same temperature. Yeah, this is solid, -3, -2 degrees. So you see that the temperature drops very slowly, so it doesn't make any sense. No, let's say this is like 1 degree gain, and we now here putting in 60 extra watts of power into the system, almost 60, 50, sorry. So 50 extra watts power roughly into the system. I mean the Peltier plus the air cooling, and then for 1 degrees this huge mess, because I mean this is also an expensive cooler and stuff like that, so it just doesn't worth it. So I hope this is convincing enough. And you see that I'm pumping so much heat. This is like, I don't know, 150 watts plus the small amount of heat. It's just crazy. So I turn this off. Because it's very noisy. What we could see now is we could see how quickly this goes back to the previous temperature, and also this, how quickly it freezes. So you can see that the temperature at least went down. And then this started to climb up, so it went up already 0.7 degrees quite quickly as compared to the speed of the cooling with that. I think I will wait until this freezes entirely, these droplets, and then I will stop this experiment. But again, there's no point of debating on this topic, because you could see the results, and I already, let's say, forecasted it, because I have some experience with these Peltier coolers, and then I know that these things cannot be used in this kind of way, so they should not be used. And I will show actually how you should use them in a more proper way to actually make use of them. But that's not this video's topic. But I hope that this was convincing enough to you that that idea will not work. And now we are at 36 degrees, so the temperature of the water is just going and going more and more up. So yeah. So regarding the temperatures, -10, so this is now at the original position, let's say. The thermometer shows -6. The thermometer here shows 27.5, so the temperature of the room here went up a little bit. This guy shows 27.2, so the room temperature again went up a little bit, because of course now we are heating it with these kind of Peltier heaters. And then here in the corner, on the other side of the radiator, it's 34.7, so went up. And then here you can see that the water is 36.2. So we pumped a lot of heat inside or into this water as well, because we increased the temperature of it by 11 degrees almost. So that's a lot of heat. So yeah, this is not how you use a Peltier cooler, once again. and you cannot really use it for CPU cooling. That's a crazy idea, because these things cannot really transfer the heat in a way that, for example, a real CPU cooler equipped with a set of heat pipes. So this is not a good idea. So I hope that this video was helpful. I hope you like this experiment. If you have any other ideas for experiments and it's not too difficult to create some setups for realizing that experiment, I would be glad to do them. So if you have any good ideas, then let me know, and don't forget to subscribe. That helps me a lot. Also, don't forget to visit my website, which is curiousscientist.tech, and see you in the next video.